Hello and welcome to your first mini lecture for this course. So mini lectures are a way that we can spend about 15 minutes of me talking with you about some of the important concepts, but they don't replace reading the book and doing the other work as well. I can't cover everything in 15 minutes. So the way this will work is I will pick a topic, record a mini lecture like this, and then put it up on YouTube. You will watch the mini lecture, and then after this is over, there are some response questions on eCollege that I would like you to do. These response questions are just meant to see if you understand the concepts that I've covered and to perhaps give you a couple of challenges now and then to see if you how deeply you understand. These responses are graded by whether or not you complete them, not by whether or not you get the answers right. So in this first mini lecture, we will be covering Chapter 1, Section 1 in your textbook, which is covering the size scales used in astronomy, some basic definitions of some objects that we'll be talking about throughout the semester. Of course, we'll go into deeper definitions later. And finally, some size scales and relative size scales. What's bigger than what fits inside of what, just so that we're all on the same page with our understanding and knowledge. Numbers in astronomy tend to be either extraordinarily large, like when we talk about distances between objects, or we talk about masses of things like the sun, or they can be incredibly small if we're talking about the nuclear reactions going on inside the sun. And so because of this, astronomers use scientific notation. Now, scientific notation is something that I assume that you have covered in high school or in other science classes. If you don't remember it very well, pretty much everything you need to know is in Appendix 1 of your text, or I've also put some links to the Khan Academy on eCollege under Unit 1, and that those videos cover the basics of scientific notation. But the important thing to keep in mind is that scientific notation uses powers of 10, or how many times we need to multiply 10 by itself, in order to write large numbers. So instead of writing 1,000, a 1 with 3 zeros after it, we can write 10 to the third. Now that doesn't save a lot, but when we get to things like the size of the sun, which are the mass of the sun is 10 to the 27 kilograms, we don't have to write 27 zeros following a 1 just to write the mass of the sun. Certain powers of 10 have prefixes that we append to the unit in order to make it a little easier to say. So for example, a meter is about a yard. If we wanted to measure the distance between Commerce and Greenville in meters, we would get something around 15,000 meters. And we can shorten that by using the prefix kilo, which means 1,000, and we can say that it's 15 kilometers or kilometers. A mega means 1 million. A giga means 1 billion. So a gigabyte is 1 billion bytes of information. And we can go the other way too for small numbers, like a thousandth of a meter is a millimeter. 1 billionth of a meter is a nanometer. So when we get to talking of wavelengths of light and we talk about micrometers and nanometers, you can refer back to this if you need to for what those numbers mean. So in everyday life, we pick convenient units to make measurements. So for example, if we're measuring salt for a recipe, we might use a teaspoon. You could measure how much salt you need in gallons, but it'd be a tiny fraction of a gallon. That'd be kind of silly to do that. We measure the size of a room in feet or in yards. You could measure the size of a room in miles, but no one would ever do that. We measure distances between cities in miles. Again, you could do it in inches, but nobody tells you how far it is from your house to Fort Worth in inches. We would always use miles. So astronomers do the same sort of thing. We could always use a single unit, and the primary unit of measurement, or the official unit of measurement, is a meter. But no astronomer is going to measure distances in meters all of the time. We pick more convenient units depending on what we're talking about. And the units that astronomers tend to use, well, we do use meters for small things. 1 meter is about 1 yard. We'll use kilometers. 1 kilometer is about 6/10 of a mile. Kilometers are good for measuring distances that we would measure in miles if we were using English units. For larger objects or larger distances, we often will use something called an astronomical unit, which is the average distance between the Earth and the Sun. And the largest unit astronomers use is something called a light year, which is the distance that light travels in 1 year. Again, we could use meters for all of these, but we pick something a little more convenient so that we can talk about a few light years and not a few times 10 to the 16 meters. So let's start by defining some objects and their sizes. We'll start with the smallest object we're going to deal with in this class, which is planets. Planets are objects that orbit stars, and most of the light from planets is reflected from their parent star. We see the Earth or we see the Moon because the Sun shines on it, not because the Earth or the Moon creates its own light. Size scales of planets: the Earth is 13,000 kilometers. You might call something a fraction the size of the Earth, like Pluto, a planet. That's around 1,000 kilometers in diameter. The largest planet in our solar system, and indeed about the largest a planet can get overall, is something the size of Jupiter, which is about 10 to the 8 meters, or 100,000 kilometers, roughly. So we usually will quote planet diameters in kilometers, because we get decent units, 13,000, 140,000. And typical planets range in size from about 10 to the 6 to 10 to the 8 meters, about a factor of 100 in size. Stars tend to be larger than planets. Stars are glowing balls of plasma. They generate their own light, and that energy comes from nuclear fusion. So our Sun is a star. Our Sun is 1.4 million kilometers across. There are some stars visible now in the winter, which we'll learn in our lab next week. Betelgeuse and Rigel, they're in the constellation Orion. These stars are larger in diameter than the Sun. Rigel is about 110 million kilometers, so about 100 times bigger than the Sun. Betelgeuse is a true giant star. It's 1.7 billion kilometers in size. And again, notice that we are using kilometers for these sizes. Most stars are around the size of the Sun, a little smaller, a little larger. Giants like Betelgeuse are very rare. And so we're going to use kilometers to refer for star diameters. Star diameters range in size from about 10 to the 8th meters, that's a little bigger than Jupiter, to 10 to the 12 meters, something the size of Betelgeuse. A solar system, or more properly a planetary system, is a star and its family, so everything that orbits around the star. That can be planets, that can be comets, that can be asteroids, it can be even other stars that, if you have two stars that are orbiting each other, those would be a planetary system. And so here's an artist picture of our solar system, not to scale, nowhere close to scale. The typical size of a solar system from one side to the other is about 100 astronomical units. What's an astronomical unit? It's the average distance between the Earth and the Sun. So the Sun is 150 million kilometers away from the Earth. That's 93 million miles. And we will call that one astronomical unit. The solar system itself, 100 times that size all the way across for most every planet and asteroid and comet that we see. There are a few objects that are a little further out, but if we want to talk about typical sizes, 100 astronomical units, a good size, and that's around 10 to the 13 meters. The nearest star to the Sun is actually a triple star system, 3 stars in orbit around each other, and that's called Alpha Centauri. To our eye it looks like a single star, so it gets one name, Alpha Centauri, but there are 3 stars there. Those 3 stars are a little over 4 light years away from the Sun. Now, a light year is the distance light travels in 1 year. It's about 10 to the 16 meters, and that's 63,000 astronomical units. Our solar system is about 100 astronomical units in diameter. The nearest star to our own sun is 600 times further away than that. So again, a light year is a distance, it's not a unit of time, and typically in our corner of the universe, stars are a few light years apart. Sometimes they're closer, sometimes they're further. Some stars, not all, but some stars are in something called a star cluster. A star cluster is a group of stars that are bound together by gravity, and they move together through space, but they're bigger than a solar system. But in a star cluster, you can have 1,000,000 stars in a region of space that's 150 light years across, not 150 astronomical units, but 150 light years, much bigger than that. Here's a picture of one star cluster. It has a name, Messier 13. We'll talk later in the semester where this name comes from. And these stars are all bound together, moving through space in a region about 150 light years across. Going larger yet, we get to galaxies. Galaxies are collections of stars and star clusters and dust and gas and then black holes and a few other objects. Galaxies tend to be very large, so whereas stars are a few light years apart, star clusters are 100, 150 light years across. A galaxy like the Milky Way, or like this one, which is called the Sombrero Galaxy, are 100,000 light years across, about 10 to the 21 meters. So it takes light 100,000 years to get from one side of this galaxy to the other side of the galaxy. Some galaxies are in clusters, and galaxy clusters are similar to star clusters in that they're families of galaxies bound together by gravity. But galaxy clusters are absolutely ginormous in size. Here's a picture of one galaxy cluster. It has a name Abell 1689, which means it's the 1639th entry in a catalog of galaxy clusters put together by a scientist named George Abell. And this galaxy cluster is 3 million light years across. So the big galaxies here are 100,000 light years across. And this entire thing is 30 times bigger than that, 3 million light years across. And that's about 10 to the 22 meters. Finally, the largest thing we're going to talk about is the universe. The universe contains everything that we can ever possibly see and detect. And so the universe contains galaxy clusters, which are made out of galaxies, which include star clusters, which have planetary systems at the middle of which is a star. You see we have a bit of a nested thing here. The whole universe is about 13 billion light years across. Distances get murky when we're talking about something the size of the universe because of weird effects from Einstein's relativity that I hope we'll get to toward the end of the class. 13 billion light years is about 10 to the 26 meters. So that's a 1 with 26 zeros after it. So what I would like you to know is I would like you to know what unit we use to measure each object. We use kilometers to measure the sizes of planets and stars. We use astronomical units to measure distances between planets and the sizes of solar systems. We use light years to measure the distances between stars. So that's one thing I would like you to know. The other thing I would like you to know is that the universe is nested, sort of like this, and I'd like you to be able to put things in the proper order. So from smallest to largest, we start with a planet like the Earth. The Earth is in a solar system which has several other planets and a star in it. Our solar system is just part of a much larger group of stars called the Milky Way galaxy. Our galaxy is in a small group of galaxies. There are a few others nearby. We're not in a galaxy cluster, but if we had thousands of neighbors we would be. And galaxy clusters are part of the universe. So from small to big, from the Earth up to the universe. I'd like you to be able to put things in that arrangement. This slide is a summary of the objects that I'd like you to be able to put in size order from smallest to biggest, what unit we use typically to measure the size of each object, and some typical sizes for each object. I don't expect you to memorize the size in meters, but I put that here so that you can see in a single unit without having to worry about, oh, I forget how many meters are in a light year. You can see here how they scale, just that we are going from smallest at the top to biggest at the bottom. So planets and stars are measured in kilometers. Planets have sizes of a few thousand to 100,000 kilometers, while stars start at about 100,000 kilometers and go up to 1 billion kilometers. The distance between the Earth and the Sun, that is 1 astronomical unit. That's its definition. And so anything that's the size of our solar system, distances between planets, all the way across a planetary system, we measure those in astronomical units. And our solar system is roughly 100 astronomical units in diameter. Distances between stars, if you're in a backwater of the galaxy like we are, tend to be a few light years. 1 light year is the distance that light travels in 1 year. It's several tens of thousands of astronomical units and 10 to the 16 meters. So light years are the largest unit we're going to use. If you are in a star cluster tends to be about 100 light years across, maybe 50 if it's small, maybe 150 if it's big. Galaxies are larger yet, and galaxies contain everything above it. Galaxies contain star clusters, contain individual stars, contain planets, contain planetary systems, contain comets. Galaxies have it all. They are larger than star clusters by far. Galaxies tend to be somewhere between 10,000 and 100,000 light years across. Galaxies can be in clusters themselves. If a galaxy is inside it, obviously the galaxy cluster must be bigger. It can be 1 to 10 million light years across. And finally, the largest thing, the universe, contains everything that we can see or detect or study. And the universe is about 13 billion light years in radius from us to the edge of the universe. Alright, that completes this first mini lecture. So now you should continue on, if you feel like you understand this, you should continue on to the mini lecture response questions for this mini lecture.